Hello. So, till now what we have discussed is the different classification or recognition techniques of patterns as well as different clustering techniques of patterns. So, the patterns that we have discussed so far, they are actually static patterns, that is the patterns which do not have any temporality in it. So, if I have a set of feature vectors which are static over time, then I can either classify those feature vectors or I can cluster those feature vectors. Today what we are going to discuss is the classification of temporal patterns or patterns which actually unfolds in time. So, what do we mean by the patterns which have temporality or the patterns which unfolds in time? Let us take for example, a speech signal. In suppose I want to recognize a word, a spoken word, say cat. So, if I simply write cat, C A T. So, if I want to recognize this word cat as it is spoken, you find that this word cat, it can be broken into three different phonemes. So, the first phoneme is say ka, second phoneme is a, and the third phoneme is ta. So, I can represent this as the first phoneme which is ka, then a phoneme a, and then a phoneme ta. So, if I utter these phonemes as given in this sequence ka, a, ta, I pronounce the word cat. Whereas, if I simply alter the temporal sequence of these three different phonemes only, suppose first I utter a, then I utter the phoneme ka, and then I utter the phoneme ta. It simply becomes act, right. So, the word that I pronounce in this case is act. So, though the phonemes are same, but they are uttered in a different sequence in time. Okay. So, as the same phonemes are uttered in different sequence in time, you find the word that is being pronounced, the word itself changes. So, this is a kind of pattern which is a temporal pattern. So, when we talk about the problem of speech recognition, when we talk about the problem of speaker recognition or any signal which varies with time, say for example, some system identification task, there we get a signal where the signal varies with time, it is a temporal signal. So, these are the examples of temporal patterns, so the patterns which actually unfold in time. Similarly, coming to our vision context of vision applications, we can have the different applications of say gesture recognition. So, we want to identify whether a person is running or the person is walking, the person is crawling. Okay. So, that these different kinds of acts, that is running, walking, scrolling. So, we want to classify or we want to recognize these different kind of tasks, or possibly all of you are aware of sign language. In case of sign language, you find that it is also the sequence of hand gestures, the different hand positions, which actually convey the meaning of the information. This convey the information to the others. So, that particular sign language, this is also an example of temporal pattern. So, today what we are going to discuss is how to recognize some temporal patterns or how to classify such temporal patterns. So, the kind of tools that we will use for such temporal pattern recognition, is something which is similar to a sequential machine or finite state machine, which all of you might have done. I hope all of you have done during your digital circuits course. So, what is a sequential machine or what is a finite state machine? In case of sequential machine or a finite state machine, we actually define a finite set of states, okay? And a machine can be in any of the states at any given time instant. And at the same time, we also have a set of outputs. So, in any state, when it makes a transition from one state to other, it outputs a symbol. So, we have a set of states and a set of output symbols. So, we can say that at time instant t, the machine can be at state say omega t, and at time instant, the previous time instant, the machine can be at state. So, at time instant t minus 1, the machine can be at state omega t minus 1. So, in case of a sequential machine or a finite state machine, the state of the machine at time state t is directly influenced by the state of the machine at time step t minus 1. So, there is a transition from state omega t minus 1 to the state omega t. So, the state of the machine at time step omega t is influenced by what is the state of the machine at time step t minus 1. So, let us just try to briefly review what we had in case of a sequential machine or a finite state machine. So, in case of a sequential machine, it has a finite set of states say S, which is actually set of states and O, which is the set of outputs. So, when we have this set of finite set of states, one of the state is called an initial state and one of the states is a final state or an absorbing state. So, we can have out of these sets, one state is an initial state and one state is final state, or it may also be called absorbing state or accepting state. And the set of outputs is actually the set of symbols which the machine outputs, or visible symbols which can be measured or it can be observed when the machine makes a transition from one state to another. And if you remember, if this set of output symbols is limited to only two symbols, that is either 0 or 1, then this finite state machine is called a finite state automata. So, a finite state automata is nothing but a sequential machine or a finite state machine which outputs only one of the two symbols, one of them is 0 and the other one is 1. So, let us just take one such finite state machine. Suppose I have a finite state machine which has got 3 states. One is S1, one state is S2 and the other state is S3. And suppose out of these 3, S2 is my final state or absorbing state and S1 is the initial state. Okay. Now, along with the set of states S and the set of outputs O, there is another set which is I, that is the set of inputs. So, the machine makes a transition from one state to another state with some input which is actually the trigger. Okay. So, in this sequential machine having 3 different states, I have assumed the state S1 is my initial state, S2 is my final state and S3 is any other state. So, the machine can make a transition from state 1 to S2 and give an output, let us say 0. It can make a transition from S1 to S3 and give an output which is say 1. It can make a transition from S3 to S2 and it can give an output 1. It can also make a transition from S2 to S3 and for this transition it can output a output symbol which is 0. It is also possible that the machine will have a self transition, that there will be a self loop, and in this case I can have something like this. From S2 I can have a transition to S2 itself and for that it will output a symbol let us say 1. Okay. So, given such a sequential machine and the outputs which are emitted by this machine whenever it makes a transition from one state to another state, and over here as I have assumed that S1 is my initial state and S2 is the final state. So, you find the kind of the outputs which are actually accepted by this machine or the kind of or the sequence of outputs which are generated by this machine, that can be 0, 1, it can be 1, 1, 1, it can be 0, then 1, then 0, then 1, then 1 and all these sort of things. So, the kind of sequences which is accepted by this machine will be say 0, as with output 0 the machine is making a transition from S1 to S2 and S2 is the accepting state. It can be 0 followed by 1, because with 0 we are making a transition from S1 to S2 and then in S2 it can make transitions within S2 to S2 with an output equal to 1. So, that is still in accepting state. So, I can also accept a string 0 1. I can accept a string 1 when the machine makes a transition from S2 to S3, then it makes a transition from S3 to S2 with an output 1. So, 1 1 there is a string which will be generated by this sequential machine, it will also be accepted by this sequential machine. I can also have 1 1 0 1, this is also an accepted sequence. So, I can have a number of sequences of such output symbols which are accepted by this machine. But you find that if I have a symbol say 1 1 0. So, from the initial state the machine comes to state S3 with an output 1, from S3 it goes to S2 with output 1, from S2 it comes to S3 with output 0, but S3 is not an accepting state. So, this symbol or this sequence of symbol does not terminate the machine in an accepting state. So, as a result, this symbol will not be accepted by this machine, or this sequence of symbols will not be accepted by this sequential machine. Okay. So, because for acceptance of a sequence of symbols by a sequential machine or a finite state machine, with the sequence must terminate in an accepting state. So, this sequence 1 1 0, this is not accepted by this sequential machine. This is not accepted. Okay. So, this is what I have a sequential machine, and in case of sequential machine, the probability of transition from one state to another, it depends upon an input. So, for example, here if I give an input say 1, it moves to the state S 2 with an output 1, but if my input is 0, it moves to state S 3 with an output 1. So, with 1 as input, the machine moves from state 1 to S 2 with an output 0. If the input is 0 in state S 1, the machine moves from S 2 to S 3 with an output 1. Okay. So, this is what a sequential machine or a finite state automata, if the set of output symbols is limited to 0 and 1. So, a tool which is similar to this sequential machine or very similar to this finite state machine, which is used for temporal pattern recognition, is called a hidden Markov model. So, what we will discuss today is what is called a hidden Markov model, or in short it is written as HMM. So, as we said that this hidden Markov model, which is used for temporal pattern recognition, is very similar to the sequential machine or the finite state machine. That is, this hidden Markov model will have a set of states, and the hidden Markov model, the machine can be in any of the states at a time instant t. Okay. So, suppose this at time instant t, the machine is in state say omega t, and what I can have is, as the machine moves the transition from one state to another, that is from time instant t to time instant t plus 1. So, from t to t plus 1, the machine makes a transition, or HMM makes a transition from state omega t to state omega t plus 1. So, at time step t, HMM was in state omega t. At time step t plus 1, at the next time step, the machine is in state omega t plus 1. So, there is a transition from omega t to omega t plus 1. And because the machine makes transitions from one state to another in different time steps, so the machine generates a sequence of states. Okay. And a sequence of states, a sequence of length say capital T, is usually represented as omega capital T, which is nothing but a sequence of states omega 1, omega 2, omega 3, continues like this up to omega t. So, it simply says that at t equal to 1, the machine was in state omega 1. So, this omega 1 may be any of the permissible states of the machine. Okay. Similarly, at time step 2, the machine makes a transition from omega 1 to omega 2. So, this omega 2 again may be any of the permissible states of the hidden Markov model. So, this way over a total duration of capital T, the machine moves from one state to another, and the sequence of steps or the sequence of states through which the machine moves, this sequence is represented by this omega t. So, it is a sequence of states of capital T number of states through which the machine moves, and this sequence is nothing but omega 1, omega 2, omega 3 up to omega t. So, this is the state in which the machine was at time step 1. This is the state in which the machine was at time step 2 and so on. So, this is I have total capital T number of states. So, for example, if I have a machine with say states omega 1, omega 2, omega 3. So, these are the states of the machine. Okay. Now, you find the difference between this omega 1 where 1 is put within parenthesis and this omega 1. This is a particular state of the machine. Omega 1 is one of the states, as the machine is having 3 states omega 1, omega 2 and omega 3. Whereas, when I write in this form, it is one of these states in which the machine was at time step 1. So, please note the difference between these two notations. And suppose I can have a sequence of states of length say 4. This may be say omega 1, omega 3, omega 1, omega 2. So, this may be my sequence of 4 states. So, the machine moves from one state to another in this particular sequence. So, at t equal to 1 or omega 1 was this omega 1, at t equal to 2 the omega 2, the state of the machine might have been omega 3. At t equal to 3 in the third step, the machine might have been in state omega 1. In the fourth step, the machine is in state omega 2. So, these are the 4 states through which the hidden Markov model makes a transition. Okay. So, as I have 4 different states, so this is a sequence of length 4 which is usually represented as omega 4. And here again you find that it is not necessary that every state, a single state has to appear only once. In a sequence, a state can appear more than once in different order. So, here you find that this omega 1 and omega 1, these two states appear twice. So, it means that from omega 1 the machine has made a transition to omega 3, from omega 3 again it has made a transition to omega 1, from omega 1 again it has made a transition to omega 2. Now, this production of state sequence in case of a hidden Markov model is described by a transition probability. So, the transition probability is something like this. The probability P that the machine makes a transition to state omega t plus 1 to state omega j at time step t plus 1, given the machine was in state omega I at time state t. So, what is the probability that the hidden Markov model will make a transition from omega I, which is the ith state, to state omega j, if the machine was in state omega I at time step t, and the machine moves to state omega j at time state t plus 1, that is at the next time state. So, the probability of this transition, that the machine makes a transition from state omega I at time state t to state omega j at time state t plus 1. This is what is given by the transition probability Aij. Compare with this our sequential machine. In case of sequential machine, we said that depending upon the input, the machine makes a transition from one state to another. So, if my input is 1, the transition probability from S1 to S2 is equal to 1. Whereas, if my input is 0, the transition probability from S1 to S3 is 1. So, this probability it will make a transition from S1 to S3. But if my input is 0, the machine cannot make a transition from S1 to S2. Similarly, if the input is 1, this sequential machine cannot make a transition from S1 to S3. So, that is the kind of restriction we have in case of a sequential machine. Whereas, in case of hidden Markov model, from state omega 2, the machine make a transition to state omega 1, it may make a transition to state omega 3, it may make a transition to state omega 5. So, all these transitions are possible and there is a transition probability that it makes a transition from omega 1 to omega 3. There is a probability that it makes a transition from omega 1 to omega 5. There is a probability that it makes a transition from omega 1 to omega 10 and all this. So, from any state at any instant of time, it can make a transition to any of the other states or to this state itself with a finite probability of transition. So, that is what we are saying over here, that if the machine was in state omega I at time instant t, then the probability that it will make a transition to state omega j at time instant t plus 1 is given by Aij. So, this is the probability of transition from state omega I to omega j. It is also possible that the machine will make a transition from omega j to omega I. So, the probability of transition is actually given by Aj I. This is the probability of transition from state omega j to state omega I, and the probability of transition from state I to state j is given by Aij. And in general, this Aij and Aji they are not equal. That is, the transition probability from state omega I to omega j may not be same as the transition probability from omega j to state omega I. Okay. So, these different transition probabilities will actually define the different hidden Markov models. Okay. So, when we design a hidden Markov model or when we go for training of the hidden Markov model, the major task of training of the hidden Markov model is learning these transition probabilities Aij, which we will see later on. Now, suppose you are given a particular hidden Markov model. Okay. So, a hidden Markov model which can recognize a particular temporal pattern. Okay. So, we usually represent such a model by a symbol say theta. So, this theta represents a specific hidden Markov model. Okay. And we have say for example, a machine, this particular hidden Markov model theta has say 3 different states. One of the state is omega 1, one of the state is omega 2 and the other state is omega 3. Okay. Now, when we have such a kind of hidden Markov model having a number of different states, one of the state is an absorbing state or an accepting state. The concept is, once the model moves to that particular state, the model cannot come out of that state. However, from any of the other states, the model can make a transition to that absorbing state, but once in absorbing state, the model cannot come out of it. We will come to the utility of such a specific state, which is an absorbing state or an accepting state or a final state later on. Okay. So, suppose this machine has this three different states given by omega 1, omega 2 and omega 3, and let us represent this as, say I have state omega 1, I have state omega 2 and I have state omega 3. So, this machine can make a transition from omega 1 to omega 2 with a probability of transition which is given by A 1 2. It can make a transition from omega 2 to omega 3, omega 2 to omega 1 with a probability of transition given by A 2 1. It can make a transition from omega 1 to omega 3. Here I will have probability of transition which is 1 3, A 1 3. It can make a transition from omega 3 to omega 1 with probability of transition A 3 1. It can make a transition from omega 3 to omega 2 with probability of transition A 3 2, A 2 3. It is also possible that it will have a transition to the same state. So, over here omega 2 to omega 2, here the probability of transition will be A 2 2. Similarly, here the transition from omega 1 to omega 1, I can have two different states consecutively. I mean same state appearing successively. I can also have similar such a situation. So, this transition from omega 1 to omega 1 which will be represented by A 1 1. Similarly, transition from omega 3 to omega 3 itself which is over here, which will be written as A 3 3. Okay. So, suppose I have a hidden Markov model specified by theta, and this hidden Markov model let us say has 4 different states omega 1, omega 2, omega 3 and omega 4. So, I have 4 different states. Okay. So, I have a model theta, that is the hidden Markov model having 4 states omega 1, omega 2, omega 3 and omega 4. Okay. And suppose we have been given a sequence of states, so sequence of 6 states omega c, where this sequence is say omega 1, omega 4, omega 2, I can have omega 2 again, I have omega 1, omega 4. So, this is the sequence of states to which the machine makes a transition. Now, given this, I can find out the probability that machine theta has made this sequence of transitions. Okay. So, how I can do it? So, what I have to find out is, I have to find out what is the probability p omega 6 given theta, right. So, when I have this hidden Markov model theta, that means I have the sequence of states, I also have the complete table or probability of state transition table. That is, I have all the aij's for all values of I and j. That is what specifies a hidden Markov model. So, suppose this theta is specified by these are the states, and I also have aij which is to be learned, but once the model is specified, I have the complete set of aij for all values of I and j. So, given such a machine theta and given this sequence of states, that is machine makes a transition from omega 1 to omega 4, omega 4 to omega 2, omega 2 to omega 2 again, omega 2 to omega 1 and then omega 1 to omega 4. So, what is the probability that this model theta has made such a sequence, has transited through such a sequence of states? So, effectively what I want to find out is what is p of this omega 6 given theta. And you find that this p of omega 6 given theta is nothing but the probability of transition from omega 1 to omega 4, which is nothing but A14, then probability of transition from omega 4 to omega 2. So, this multiplied by A42, which is the probability of transition from state omega 4 to omega 2. Then the probability of transition from omega 2 to omega 2 itself. So, I have A22, which is the probability of transition from state omega 2 to omega 2. Then from omega 2 to omega 1, which is nothing but A21, and then the probability of transition from omega 1 to omega 4, which is A14. Okay. So, the probability that this model theta has made a transition through a sequence of states is nothing but the probability of transitions between successive states. So, it is the product of the probability of transition between successive states. So, the machine this theta will have these transitions. The probability of that is p omega 6 given theta is nothing but p omega a omega 14, which is the probability of transition from state omega 1 to state omega 4, multiplied by the probability of transition from omega 4 to omega 2, that is A42, multiplied by probability of transition from omega 2 to omega 2 itself, which is A22, multiplied by the probability of transition from omega 2 to omega 1, which is A21, multiplied by the probability of transition from omega 1 to omega 4, which is A14. So, this is the probability that this machine theta has made a transition through this sequence of 6 states as specified by this omega 6. Okay. So, that is fine. I mean, I have a model, the model has a number of states and the machine makes a transition through a sequence of states over time. And what is the probability that the machine has generated or has transited through a given sequence of states? I can compute that. I can compute that probability. Now, what are these states actually? Let us say that I have again in with an example to my speech recognition. I have two different words, one is the letter, other one is alter. Okay. So, you find that they use the same phonemes. Okay. One is letter, other one is alter. If I break them into phonemes, this consists of a sequence of phonemes la, ta, again and ra. Whereas, in case of alter, this is this is la, this is ta, this is again and this is ra. So, you find that it is the same set of phonemes, but occurring in different order in time sequence, and that is what makes the difference between letter and alter. So, I can say that in my hidden Markov model, every state corresponds to one such phoneme. Okay. Every state will correspond to one such phoneme. So, as here I have 1, 2, 3 and 4 different phonemes, because this phoneme and this phoneme is same. So, I have 4 different phonemes. So, I can have 4 different states to model this particular spoken word. Okay. Similarly, the same different states, but occurring in different sequence will generate this spoken word alter. So, this may be the different states, and if I say that the first phoneme L, la, corresponds to state omega 1 or corresponds to state omega 2, tau corresponds to state omega 3 and Ra corresponds to state omega 4. Okay. In that case, the probability P letter, that is the sequence, given theta, that is my model, it will simply be, here you are making a transition from La to A. Okay. So, omega 1 to omega 2. So, it will be A 1 2 multiplied by A 2 3 multiplied by again from ta to a. So, 3 to 1 A 3 1 multiplied by a to ra, right, sorry, ta to a. So, 3 to 2 multiplied by a to ra. So, 2 to 4. So, this is the probability that this hidden Markov model will generate the spoken word letter, or it can recognize the spoken word letter, is this. Similarly, the probability that it has generated alter given theta, this will be simply, this is R to La. So, omega 2 to omega 1. So, A to 1 multiplied by La to ta, La to ta, this was ta. So, A omega A 1 3 multiplied by ta to a again, ta to a. So, A 3 2 multiplied by a to ra. So, that is A 2 4. Okay. So, you find that these two probabilities are same, A 3 2, A 3 2, A 2 4, A 2 4. But these two, A 1 2, as we said, it may not be same as A 2 1. Similarly, A 2 3 may not be is not usually not same as A 1 3. So, because of this, the probability that this theta generates letter and the theta generates alter, they will be different for a given hidden Markov model theta. Okay. So, if I actually train a hidden Markov model to recognize the word letter, the spoken word letter, and then when I have the same word letter which is spoken with these different phonemes, then the probability that the theta will return for the word letter will be more than the same theta which will return the probability for the spoken word alter. So, once you train a hidden Markov model with a particular sequence, the model actually learns the probability of transition from one state to another. For another word, another spoken word, these probability of transitions may not match, though the states might be same. So, that will generate a lower probability of generation or lower probability of occurrence. So, this is how, given a model and given a sequence of states, I can find out what is the probability that the machine has transited, or the hidden Markov model has transited through that given sequence of states. Now, as I said that in this hidden Markov model, there is a specific state which is an accepting state or absorbing state, and this specific state is usually represented by the symbol omega 0, right. And as we said that once this hidden Markov model enters the state omega 0, it cannot come out of that state. However, it can make infinite number of transitions within that state. So, as a result, I will always have A 0 0, that is the probability of transition from state omega 0 to itself will always be equal to 1. Whereas, because I can't have a transition from omega 0 to any other state. So, I will always have a 0 I is equal to 0, because from omega 0 I cannot make a transition to any other state omega I. So, a 0 I will always be 0 for all I. Okay. So, this is what is very important. I will have a 0 0 equal to 1, because from the final state it can make infinite number of transitions within the same state, but from the final state it cannot make transition to any other state. So, as a result a 0 I for all states I will be equal to 0, whereas a 0 0 will be equal to 1. Right. Now, we find that we have so far discussed this hidden Markov model with respect to states. Now, these states are the ones which are not really visible, or it cannot be observed by the perceiver. What is visible or what is observable to the perceiver is certain set of symbols which can be observed or which can be measured, right? Whereas, the states are not really visible. I mean, the same thing applies to our sequential machine. Okay. These states S1, S2, S3, they are not really observable. I cannot observe them, but what I can observe is the output which is emitted by the machine. So, I can observe this output 1, I can observe this output 0. Okay. So, these are the outputs which are really observable. The state is not really observable. So, in the same manner, in case of this hidden Markov model, the states that we have talked about, these states are not really observable. But what is observable, or what can be measured, based on which we can take a decision that whether a given word, a spoken word, or a sequence of actions belongs to a particular class or belongs to a particular category, this classification has to be done based on observable symbols. Okay. I cannot observe the states through which the machine will transit. So, along with the states, I also have to have a set of observable symbols. Okay. So, this set of observable symbols is actually given by a set, say V. This is the set of observables. Okay. And accordingly, I can have a visible state which is given by V t. Okay. So, for hidden Markov model, I have two types of states. One set of states which cannot be observed, which are not visible or hidden, those states are hidden, which are represented by omega t, and a set of states which are observed, which can be observed, which can be measured, that is the visible state. So, at a time step t, the machine can be state omega t, which is hidden state, and it can emit an observable state which is given by V t. And as we have done in case of the states or the hidden states, that the machine can transit through a sequence of hidden states, and given a model I can find out what is the probability that the model has transited through such sequence of hidden states. In a similar manner, for the visible states, I can have a sequence of visible states. Okay. So, a sequence of visible states of length capital T, which is given by V t, in the same manner it is represented by V 1, that is visible state which is emitted by the machine at time step t equal to 1. Okay. Similarly, V 2, so this is a visible state which is emitted by the machine at time step t equal to 2. Similarly, V 3, and it continues up to V t. So, this is the sequence of visible states or visible symbols which are emitted by the machine at different steps in time. Okay. And this is actually such sequence of observable symbols they actually constitute your pattern or temporal pattern. Okay. And I have to recognize such temporal pattern using hidden Markov models. So, that is the task that we have. So, as we have two different sets of states, one is the set of hidden states given by omega t, and another is the set of visible states or visible symbols given by V t. And we have said that we have a transition probability A I j, that is the probability of transition from state omega I at time step t to state omega j at time step t plus 1. So, we have said that this A I j is equal to probability that the machine will be in state omega j at step t plus 1, given the machine was in state omega I at time step t. So, this was the probability of transition. In the same manner, there is also a finite probability that in the ith state or in state omega I or in state omega j, the machine will output a visible symbol or a visible state which is V k t. Okay. So, I also have the probability p that the machine will output a visible symbol V k t at time step t, given the machine is in state omega j at the same time step t. Okay. So, while in the hidden state omega j at time step t, the machine outputs a visible symbol V k at the same time step t with a probability given by p V k t given omega j t, and this probability is usually represented by B j k. So, this is the probability that the machine emits a visible symbol V k or visible state V k from state at state omega j. So, this is what is B j k. So, whenever I have a hidden Markov model, I have to have, whenever I specify a hidden Markov model, I have to have three things. One is the set of omegas, which are the hidden states, a set of v's. So, I have to have omega, which is nothing but set of hidden states, I have to have a set V, which is the set of visible states, or visible symbols. Okay. I have to have A I j, which is the state transition probability, and I have to have B j k, which is this also I can term as state transition probability, because both V and T, both omega and T, we are terming them as states. Okay. Omega is the state of hidden state and V is the state of visible state. So, this B j k I can also term as state transition probability, and this state transition probability is from a hidden state to a visible state. But actually this is the probability that my hidden Markov model emits a visible symbol V k when it is in the hidden state omega j. So, this is actually visible symbol emission probability. So, these are the 4 different items which must be specified for specification of a hidden Markov model. So, I will stop this discussion today here. In the next class, I will elaborate on this hidden Markov model and we will see that how the temporal pattern recognition can be achieved through hidden Markov models. Thank you.